Things are about to get interesting because we're going to have to go from the a written word equation into the formulas of each individual compound, put them in the right place, and then to represent the chemical reaction and then balance them correctly. So to do this, what we have for number one is zinc plus hydrochloric acid. Those are the reactants. The arrow, remember, means the reaction is going to happen. That's yields the products of zinc chloride plus hydrogen. Those are the products produced by the chemical reaction from zinc and hydrochloric acid. So the formulas are going to look like this. Um, we have zinc, which is Zn. I have hydrochloric acid, which is HCl. And then I have my arrow to represent the chemical equation. Then we have Zn for zinc. Chloride is Cl plus H. Okay, and what we need to do now is make sure, is this even correct? Because we need to follow our rules of ionics to double check. Now, Zn is not one of the diatomic elements, so it's just going to be zinc is just Zn. HCl, again, even though it's an acid, we name it like an ionic. Hydrogen has a +1 charge. Oxygen has a -1 charge. So when I cross those down, it does in fact just stay HCl. So that's all correct. Zinc chloride, Zn has a +2 charge. Again, it's one of those transition metals that always has a +2 charge, like aluminum always has 3 and silver always has a 1. Chlorine is in the 7th column of the periodic table, so it has a -1 charge. So when I cross that down there, that goes down there. My final formula is ZnCl2. So that's actually zinc chloride. Then hydrogen on the right side is one of the diatomic elements, so it does need a 2 there because, again, if we have a cloud of hydrogen gas, it's actually a cloud of H2. Many of them, but it's still just H2. So let me clean this up real quick, and we're going to make those corrections, and then we'll get started on the actual balancing. I wanted to go over that real quick just to make sure you guys all remember how to do that, and just to stress again how important it is that we do all of those parts correctly. So we have ZnCl2 and H2. So that is the correct formula for zinc plus hydrochloric acid yields zinc chloride and hydrogen. What we need to do now is figure out how to balance this thing. So the largest compound, of course, is this one right here. I'm going to balance everything to the zinc chloride. So what I notice is I have one zinc, I have one zinc. Well, okay, that's good. Not very helpful. What I have right here is two chlorines. So I need two chlorines on both sides. So the only thing I can do is put a number in the front. Remember, I cannot do this. That sure would be nice, but you're changing the compound, and therefore that is not how chemistry works. So as I doubled my chlorine in this case, I also, of course, doubled my hydrogens. So I would come over to the right side and double my hydrogens, but look, I already have a 2, which tells me we are done and it is balanced. Again, whenever you are trying to go from this side to balance one element, look at what it is, then you go back to this side, see what that is. Once you get to a point where what you're looking for is already present, you're finished. So number 1 in our example is now done. This means we have zinc plus 2 hydrochloric acid molecules yields zinc chloride and hydrogen. All right, let's try number 2. What we have here is aluminum carbide. Aluminum carbide would be, aluminum is Al, carbide is C. Okay, aluminum carbide. Let's go ahead and do the charges real quick. So, of course, aluminum is a +3. Carbide is carbon, and that's a -4. So I'm going to take that down there, move that down there. So the final formula is actually going to be, I'm just going to move it down here. This makes it a little bit easier for myself, actually, and make it Al4, oops, C3. Al4C3, that is aluminum carbide. It is going to react with water, so that's easy, I know water, H2O, to form methane. They went ahead and told us what methane is, CH4, and aluminum hydroxide. Aluminum is this, hydroxide is OH with a -1 charge. Remember, hydroxide is a polyatomic ion, so I need to find the charge of aluminum. Of course, it is a +3. So as I cross that down there and that down there, what we get for aluminum hydroxide is Al parentheses OH3. So that is the correct compounds. Al4C3, aluminum carbide, reacts with water to form methane and aluminum hydroxide, which is AlOH parentheses 3. Now that we have all that, what we need to do, of course, is balance this thing. So the largest thing that we're going to probably have the easiest time balancing to is the first compound, which is aluminum carbide. So this thing right here, again, has the most numbers. So I'm going to try to balance to that. So let's see if we could do this. What we have here is 4 aluminums. So over here, I have 1 aluminum. So I'm going to need a 4 there. So now I have my aluminums are balanced. Okay, but again, when I balance this, I also made 4 of those. Now, what you want to notice is there's already a 3 here. That's interesting. So what that tells me is that there are 3 OHs in aluminum hydroxide. There's already 3 H's. I just put a 4 in front of that, so that means I have to multiply. I have 4 aluminums, but I actually have 4 times 3, 12 hydroxides. I have 12 hydroxides, okay? Well, that's interesting. Let me go ahead and make this a little bit easier for myself. I'm going to call this HOH. And let's see, I need 12 hydroxides. So the only way to get around that is I need 12 for the OH. Okay, 12 for the OH. So now, again, if I did 12 for the OH, guess what? I also did 12 individual H's. So that tells me I need a 12 here too. So I did 12 C's. Well, what about did I do to my H's? Let's see. No, I don't need 12. Sorry. Oops, I wasn't thinking. What I needed, so I had 12 OHs here. I had 12 H's. What I need here is actually a 3. Is that not right? Because again, if I do 3 times 4, what I get is 12 H's to balance out those 12 H's. So let me erase all this, and I will talk through it one more time just to make sure I didn't lose anybody or confuse anybody worse. And so we can see exactly how this works. So what I basically did, if you follow my logic, is I started here. I tried to balance my aluminums by going with the 4 aluminums to make 4 aluminums, right? But as I did the 4 aluminums, I also made 4 hydroxides. But because there's 3, that actually gives me 4 times 3, which is 12 hydroxides. So to make 12 hydroxides, I went ahead and did 12 OHs. So as I did 12 OHs, that also gave me 12 individual H's. So what I had to do there is then go back to this side and put a 3 in the front because this 3 times this 4 gives me 12 H's. So notice I went from the left to the right, then back to the left side of the arrow, then back to the right side of the arrow. You always want to jump, think of like tennis. You're going from the left side of the arrow to the right side of the arrow, to the left side of the arrow, to the right side of the arrow, and you'll just keep going until what you need is found or just works out nicely. So that looks a little bit chaotic, but again, these are not supposed to be the easiest examples. These are supposed to be real examples. All right, I cannot erase that red for some odd reason. No idea why. Okay, well, let's go ahead and keep moving on for the sake of time. All right, for number 3, we have a solution of potassium bromide. So let me change my color. Potassium is K, bromide is Br, is mixed with a solution of barium is Ba, acetate is C2H3O2 to form potassium acetate C2H3O2 and barium bromide. Okay, whew, let's go ahead and check to make sure these are all correct before we start balancing because I don't want to mess this up. So K is a +1 because it's in the first column of the periodic table. Bromine is a halogen, so it is in fact going to be KBr. That was correct the first time. So we have KBr plus. All right, the next thing is we're going to have barium. Barium is in the second column of the periodic table, so it's a +2. Acetate, this whole thing here has a -1 charge. Therefore, when I move the 2 down here and the 1 down there, our final answer for barium acetate is actually going to be BaC2H3O2 parentheses and then a 2. We have a 2 outside the acetate because, again, we need 2 acetates for every 1 barium. Then that's going to yield potassium. Potassium, again, just like before, is a group 1 metal. Acetate, again, is also a -1. So those are going to cancel out. So our final formula for potassium acetate is, in fact, just KC2H3O2. No parentheses necessary because there's not a number after the acetate. Plus, we have barium. Barium, again, just like before, is a +2 metal. Bromine is a -1. So I'm going to take that 2 down there, that 1 down there. And what I end up with is BaBr2. That's barium bromide. So that, again, is a skill all on its own. We have to be able to figure out what the heck is potassium bromide, what is barium acetate, what is potassium acetate, and what is barium bromide. If we can't even get that part right, the balancing, again, is going to be significantly harder and almost inevitably going to be incorrect. So let me erase this just so I can get myself a little bit of space. If you guys are still confused, don't forget you guys can rewind and go back and watch that again. All right, what I'm going to try to balance to is this barium acetate because it's the biggest, has the most elements, and the most numbers. So when I look at it, I see that I have 2 acetates. I have 2 of these things. So I need to have 2 acetates. The only way to do that is to put a 2 in front of the potassium acetate because, of course, when I double that, I'm also doubling this. So now I have 2 acetates on both sides, but now I have 2 potassiums. So I'm going to come over to this side, to the left side of the arrow, and I need 2 potassiums. Okay, so I doubled this one. Guess what? I also doubled the bromine. So I'm going to come back over to the right side, and hey, look at that. There's 2 bromines. That tells me already we're done. I needed 2 bromines on the left side. I need it on the right side, but I already have the 2 bromines. So that makes me happy because I know, oops, that tells me that I am finished with this balancing. Let me go back and replace that number I erased on accident. There we go. So that is the correct balance of 2 potassium bromides for every 1 barium acetate yields 2 potassium acetates and only 1 barium bromide. Again, it's a ratio, a 2 to 1 to 2 to 1 ratio. It could have been 4 to 2 yields 4 to 2, but 2-1 yields 2-1 is the lower of the 2, right? The other one would work. You could have 6-3, 6-3, or I don't know, 12-6, 12-6, but really it's the same thing as 2-1, 2-1. So that's the correct balance equation for number 3. Number 4, we have copper reacts with oxygen to produce copper 2 oxide. Okay, so copper, Cu, reacts with oxygen to produce copper oxide. Okay, let's try this out. So, of course, copper is a metal. It's not diatomic, so it's just going to be Cu. Oxygen, on the other hand, is going to be O2 because it's one of those 7 diatomic. Remember Brinkelhoff, the Hoff, H-O-F, O is in there, so that it's going to get a 2. But it does not get a 2 here because oxygen has a charge of 2. Copper, it tells us right here, has a charge of +2. So, of course, we're going to cross those down, but don't those cancel out? Yes, they do cancel out. So our final formula is going to be nothing more than copper plus oxygen yields copper 2 oxide. There it is. So that one was actually relatively easy as long as you could recognize that the copper and the oxygen had a 2 charge. And don't forget that oxygen is also an O2. It's not just O. So again, let's try to balance this. Obviously, what I'm going to have to balance to is the oxygen. I think we've done this one before. I'm going to put a 2 here because, again, that's going to balance out my oxygens on the left side and on the right side. But as you guys know, once I double that O, I've also doubled the copper. So to get that balanced, I'm going to put a 2 there. And there we are finished. There's the balanced form of copper reacting with oxygen to produce copper 2 oxide. 2Cu plus O2 yields 2CuO. Sounds kind of funny, right? Okay, let's go ahead and keep moving on. We have number 5. Number 5 is tetraphosphorus dicoxide gas. So let me get my pen ready. Tetraphosphorus P4 dicoxide O10 gas and water reacts to form phosphoric acid. And again, they gave that to us. It's also called hydrogen phosphate. There. Technically, that would be AQ, but don't worry about that. But let me just go ahead and show it to you. That way you know you don't need to be intimidated by that, okay? So tetraphosphorus dicoxide in the gaseous form, hence the little G in the parentheses, is going to react with just water. I don't need to say it's liquid. I don't need to say it's gas. It's just reacted. They don't really tell us what form. I assume it's a liquid. To form phosphoric acid. And acid is always going to be in the aqueous state. If I had, for example, just as a little foreshadowing for something that's coming up later, if I had this hydrogen or H3PO4 in the solid state, that's called hydrogen phosphate. Hydrogen phosphate is technically not an acid. It's once you put it into water, AQ, aqueous, then it becomes an acid. So H3PO4 in the aqueous form is an acid. Now, do I need to worry about the G and the AQ when it comes to balancing? Not at all. Not at all. Do not worry about them when it comes to balancing one bit. They're just informative, but they're not obstacles to us when it comes to balancing. So I'm going to try to balance 2 is the large P4O10. H3PO4, it maybe has more elements. It has 3 elements, but look at those 10 oxygens. Yikes. So I need to make sure I'm going to balance to that big one, the P4O10. All right, so to do that, because I have 4 Ps, I'm going to go ahead and start with 4 Ps there. So that gives me 4 phosphoruses, so they're balanced, right? Let's go ahead and do the oxygens next. So when I did that, I also quadrupled my oxygens, but notice I already had 4 oxygens, so that means I need to multiply. So I have 4 Ps, I have 4 times 4, I have 16 oxygens. 16 oxygens, okay? Notice over here I already have 10, so I'm going to try to balance that. Let's see if I can put a 6 there, because this 6 plus these 10 should equal 16, right? Which again is what I have right there. So if that will work, our oxygens are now balanced, okay? Our oxygens are balanced and our phosphorus is balanced. Now we just need to double check our H's. Our H's we have, again, notice 6 times 2. So 6 times 2, of course, is 12. Over here, for our hydrogens, we have 4 times 3. 4 times 3 is also 12. So that tells me we have a balanced number of hydrogens, oxygens, and phosphoruses. This is the correct formula, balanced formula of tetraphosphorus dicoxide reacting with water to produce phosphoric acid. It would be a 1:6:4 ratio. Again, we have 4 P's on each side, we have 16 O's on each side, and we have 12 H's on both sides. Like I told you guys, it doesn't matter. It doesn't always be, it's not always 2. The P's have to balance each other. The O's have to balance each other. The H's have to balance out each other. That's just the only way it works. All right, number 6. What we have here is iron oxide, 3-oxide, reacts with carbon monoxide to produce iron and carbon dioxide, okay? I think I need to double check that first one because that sounds like an ionic. Iron, again, the Roman numeral is going to be a +3. Oxide is oxygen. It has a -2 charge. So I'm going to cross that down there, cross that down there. And what it comes out to be is Fe2O, no, that's not an O, O3. That's iron 3 oxide plus carbon monoxide. Now that's a covalent. Carbon monoxide, they're telling us it's 1 carbon, 1 oxygen. So I don't need to do anything with charges because covalents don't have charges. That is going to yield iron. Is iron one of the Brinkelhoff elements? No. Iron is a metal. It's not a divalent molecule at all. Plus carbon dioxide. Again, they're already telling us what that covalent compound is. It's CO2. So therefore, that's pretty nice. We now have our correct formula for iron 3 oxide reacting with carbon monoxide to produce iron and carbon dioxide. All we need to do now, of course, is balance. I'm going to balance, I'm going to balance to this right here because, of course, it has the most elements and the largest numbers. So let's see, we have 2 Fe's. I can start there if I want to. So I'm going to go ahead and balance out my Fe's. I'm going to put a 2 there. So our irons are now balanced. We have 2 here. We have 2 there. Okay, we have the oxygens is a little bit interesting because what we have here is 3 oxygens plus 1, which is 4. 3 oxygens here plus the 1 gives us 4 oxygens. Can we make the right side into 4 oxygens? The only way to do that is to put a 2 in the front, because again, the 2 in the front multiplied by the 1 on the bottom gives me 4 oxygens. So our oxygens are now balanced, so that's good. But darn it, what that did to me is that messed up my carbons, because I had balanced carbons. I don't know if you noticed that, but my carbons were balanced. Now they're not. So the only thing I could do now is try to fix the carbons. So I'm going to have to put a 2 here. Okay, but oh my gosh, that's going to mess up my oxygens. So I still have 3 oxygens there, but now I have 2. I'm going to add those together and I get 5. Oh boy. 5 oxygens. How do you make this into 5? Okay, you can't, because there is no multiple of 2 that's going to give you 5. So let me walk one more time through the problem that we just experienced. The problem that we just ran into is that if we start with the Fe2O3, it doesn't work. The irons can balance, the carbons already were balanced, but now the oxygens are all messed up. So again, the reason why the oxygens are messed up, just in case you didn't see it, is this is what we had before when we were just balancing the oxygens, right? Oxygens look happy here. We have, again, these 3 plus this 1 gives me 4. And then I had the 2 here. That 2 times that 2 gives me 4. So my oxygens are now balanced. But this also doubled my carbons. So my carbons need to be balanced. So I had to put a 2 here. That changes this to a 2, which gives me 5. 5 is not divisible by 2. So what do we do? Are we just messed up? Are we just going to give up and just not do this problem? Just tell them this, tell your teacher like, hey, I can't do this one. This doesn't work. No, there is a way to get around this. I'm going to go ahead and erase everything, get all the way back to the beginning, and let's see if this works. I'm going to take my largest compound and I'm going to double it. Boom. I'm automatically going to take my largest compound that I balanced everything to, and I'm going to make it twice as big. Now let's see if this works. Okay, so now that we have that, I have 2 times 2 irons, which gives me 4. So I need 4 irons there. Okay, that's pretty easy. No problem there. All right, then what I have here is 2 times 3, which is 6 oxygens. Over here, I have plus 1. That gives me 7. Okay, that's interesting. Well, I can't make this into a 7 because, again, it's a multiple of a 2. So let me go ahead and try to double that. Let's see what happens. So 2 times 2 gives me 4. So that's not going to work. Okay, let's try 3. So 3 times 2 is 6. Okay, we're getting closer. If I put a 3 there, though, wouldn't I have to put a 3 there? I sure would. That would make that 3, which would make that 9. Okay, so we have 9 and 6. That's still not going to work. So let's try changing this to a 4. So notice what I'm doing is I'm just doing a little bit of trial and error, right? Let's see if this works. 4, okay, so that's going to be 4 times 2 is 8 oxygens. 4 times 2 is 8 oxygens. What I have here is 2 times 3 is 6, plus those 4 give me 4. That gives me 10. So it kind of appears like we're chasing our tails on this one, doesn't it? Okay, so let's try 5. Let's see what this gets us. Okay, so if I have 5 here, 5 times 2 gives me 10 oxygens. I would need 5 there because there's 5 carbons. That gives me 5 oxygens, so that's still 6. This is 5, so that gives me 11. That's not it. Wow, this is getting really out of hand. Okay, so let's try 6. Okay, so 6. That gives me 6 times 2 is 12. Over here I have 6 plus those 6. That gives me 6. That gives me 12. Okay, so that actually seems to work. What we have, let me go ahead and erase all this mess and see if this works. So I have 4 irons there to go with 4 irons. Okay, so those are balanced. I have 6 carbons here to go with those 6 carbons there. Okay, that's balanced. And then I have 12 oxygens there. I have 6 oxygens here plus this 6 there, so that equals 12. So that is in fact balanced. Now, one thing that's kind of odd, even though this worked and I had to spend quite a bit of time and I had to keep, being persistent to get it to work, do you notice how this is really the same thing as a 1 to 3 to 2 to 3 ratio? 1 to 3 to 2 to 3 ratio? That tells me that's actually would have been the correct answer as well. That should have worked in addition. So let's just double check that. So I'm just really curious. Let's see, does that actually work? So I'm going to go ahead and put my formula here, Fe2O3 plus carbon monoxide yields 2 iron plus carbon dioxide. So let's just double check. Let's see, does that in fact work? Okay, so let's double check now. We have, of course, 2 irons to go with 2 irons. That's not surprising. We have 3 carbons to go with those 3 carbons. Okay, that's not surprising. Let's see if the O's work. We have 3 here plus those 3. That gives me 6. And then this gives me 6. So in fact, it does work. So in this particular case, we did not need to double the original Fe2O3, but it does sometimes work, makes it a little bit easier. We did not see that 1323 is the in fact correct balanced equation, but in fact it did work. So there it is, 1323. That is the way to balance number 6. All right, the last one, number 7, we have hydrogen. I'm gonna go ahead and do this one a little bit quicker. Again, notice H2 plus chlorine, Cl2, because they're both diatomic, Brinkelhoff, remember, and hydrogen chloride gas. Of course, Cl2 is a gas, H2 is a gas. So all 3 of these are gases. This is a chemical reaction occurring in the gaseous state. So to balance this, what I'm going to need is, I have 2 H's, 2 Cl's, so I need 2 HCl's. Done. That was easy. All right, guys. So we had some easy ones like number 7. We had some really challenging ones like number 6, and trying to work through our ways of getting around obstacles. Sometimes it's going to take a little bit of time. Sometimes you just have to keep trying. Obviously, I would do this on paper, and I would use a pencil. You do not want to use a pen because there's a lot of erasing going on, and that is normal and acceptable. Number 5 was also fairly difficult. So again, guys, this is how you balance chemical equations to follow the law of conservation of mass.